Welcome back. In the last session, we have discussed the autograd variable element of Pytorch and how to create and preserve the computational graph. We also briefly mentioned the CUDA functionality of Pytorch. Today we are going to create a linear model with Pytorch. So let us start. So first we are importing the required libraries, which is Torch library. As you remember, Torch library is the Tensor library of Pytorch. Then we are importing NN module, neural network module. Then we importing autograd from autograd variable. As you remember, autograd variable is the main building block of Pytorch computational graph, and here we're importing just numpy. So let us execute the next cell. What we do here is following. We are creating some data for our model. So first of all, we are creating x. X is just the numbers from 0 to 20. Here we use a nice feature of Python, which is list comprehension. Sorry. In the next step, we are converting this X list to a numpy array, and then we reshape it to be a column vector. If you look at the print, you see what we have created. So we have created from 0 to 19, 20 elements of X, and then we have reshaped it to the form 20 to 1. It's a column vector. Almost the same thing with Y, but Y is now the linear combination of X. So every element of Y is 5 multiplied by X, or by index I, which is the same in this case, plus 2. And then we are creating numpy array out of it of type float 32, and then we reshaped it to be a column vector. Let us have a look on at the printout. This is the linear combination, actually linear function, and the printout is again of this numpy array 20 to 1 numpy array. Now the important point. So now we are creating a linear model with Pytorch. Every model with Pytorch is created with class. So you have to create a class. It's pretty straightforward and simple, especially for those of you who has already some experience in programming, especially in object-oriented programming, like in Java or in C# or in Objective-C or whatever. You are creating classes. A class actually is a blueprint of an object. Object is a special instance of a class. So if you create a class, you create a template for an object. Object is an acting instance. So now we are creating class which we are calling linear regressor. So the name you can choose freely, whatever you like. But here's important point. We are inheriting this class from module class of neural network package of NN library. This is important point. It must always inherit from module. Every Pytorch model class inherits from module. The next, we are defining init method. Init is equivalent to a constructor in other programming languages like Java or C#. Here we don't call the class name, but underscore init underscore. It's just a flavor of Python to call this constructor will initialize the class, will initiate the class with the values which we are passing here. So we are passing here the instance of this class itself. Then we are passing input dim, input data dimension, and here we are passing output data dimension. And then we are call the super class. Super is the constructor of a class from which we are inheriting. So we are inheriting from module, and we call super is calling to the module class. Super meaning give me the class from which we are inheriting. In here we are calling the init method of the superclass. Init meaning constructor. And here, the next line of code, we are creating linear object, linear model from the superclass. We don't want to create every nitty-gritty. We are here. We just getting all those stuff from the superclass, how linear model is designed, and we are storing this in our variable which is called linear, self linear. And this class has only one method which is called forward, and for this method we are passing the instance of the class itself, and we are passing x data. So in here we see we again calling self linear, and we are printing out what linear function computes. That's it actually. And for every model which you are going to create with Pytorch, this is very similar structure which you create. So you always create a class which you are inheriting from a module, and in constructor you are passing what you are actually going to do in this special model. So in this case it's linear model, but there are a lot of other things which you can take from this NN module. For example, you see here conf1d, conf2d, whatever. So even GRU, gated recurrent unit, if you want to create a RNN, recurrent neural network of brand GRU, or LSTM, for example. You can also create LSTM cell. It's very granular. You can create a lot of things, but the structure remains always the same. So you have init, you have backward. So now we defining the input dimension. As you see, we need here the input dimension if we want to run this class. Input dimension is 1, so actually we have one column vector with 20 elements, and it has one column dimension is 1, and output dimension is also 1. And here we instantiate this class, meaning we create an instance of a class, a running object of a class, and we are passing input dimension and output dimension. This we have defined in our constructor. So we have defined that we are passing self. Self will be passed automatically from the class itself, but for input dimension and output dimension we have to pass them. So let us execute the cell. You see what is model. Model is a linear regressor which inherits from inherits from module, and has linear function in it, linear class in it, and we are passing input features dimension 1 and output features dimension 1. So this is the main building block of our regressor. Now we need to specify loss and optimizer functions, as actually in any other deep learning framework. So we specify loss function with the MSC mean squared error loss. This is also a class which is stored in module NN, neuronal network, and we specify the optimizer with SGD, stochastic gradient descent. This is in a Torch Optim package. And here we have to pass two arguments, which are the model parameters, meaning model which we have created already, and we have also to pass the learning rate, which is here 0.001. Let us print out this, execute and print out. So we have created optimizer and we have created loss function. We can also print loss function. Oops. Okay. Not so much information, MSC loss, but it's okay. So we have created both. Now we are coming to the training. And here we have only to specify the number of epochs, which I have created pretty high, 500, but our data is very small and it will be very, very fast. And then we are creating a for loop in range epochs, so 500 epochs. Now we are coming to the inner structure of this for loop, and this is very important. This is also pretty the same for any other Pytorch model. So first of all, we increment epoch, and then we are creating inputs. Inputs we have to convert to torch from numpy array, which is done here, torch dot from numpy, and we are passing the training data. And this is the data which we are passing to our autograd variable. As you remember, autograd variable is required to build a computational graph which we need to compute gradients later. So we are passing this variable and we are getting the outputs. Then we have to reset gradients with 0. So in every epoch we are resetting gradients for the optimizer. The next step, we are creating forward, so we are actually predicting. So we have already our model, we have instantiated our model, which is here, and using this model we can predict already. So we are predicting, so we are passing the inputs again. We are passing the inputs and we are getting predicted outputs. The next step is computing the loss. So now we can compute the loss. We know what are the real outputs. Here we are passing actually y real because it's y train actually. So we have defined specified y train. We know what it is, and here we just converting it to a numpy array and passing to a variable, but these are the real outputs. And here we have created the predicted outputs, and now we are specifying the loss function, and we are passing to the loss function predicted outputs and real outputs, and then it will compute loss. And then we use loss function to go backward and to compute gradients. And then we have to call optimizer step. This is actually the skeleton of every single model training in Pytorch. You will always run the same steps. Even if you want to create the most complicated neuronal network, it will be the same. And Pytorch uses also this optimization technique to optimize even the simplest model, like linear model or whatever, or logistic model. It's the same. It will always run the same steps and actually apply the same technique of optimization. And then you have to print out. Actually, in Pytorch, you will not have this convenient methods like in Keras, where you just specify what do you like to be printed out, and Keras will print out everything for you. Here you just have to write a small line of code to see the output. But this is the price for this flexibility. So you have here complete flexibility. How do you build your computational graph? You can decide at runtime what be in the graph. You can specify whether to run the tensors on CUDA, on GPU, on CPU, and everything. You can specify the sizes of the tensors, whatever you like at runtime, and you can change it at runtime. And this is great flexibility. And my opinion is that the price which you have to pay for it, that you have to run some boilerplate code, but it's not too much in my opinion. So let us execute this for loop and train our model. It's very fast. It's already trained. So we have 500 epochs, and you see that the loss decreases continuously, and then we stop by loss 0.2, and actually we have very good accuracy here. We can actually be proud of us. It's a very simple model, of course, but if you like to create something more complex, you will actually use the same structure as we have discussed here. Okay, this is the last session in our introductory sessions cycle of Pytorch. I hope you have enjoyed, and see you next time. Bye bye.